Almost every piece of digital infrastructure on Earth is currently guarded by language. This is the legacy baseline of global security, a system known as semantic networking. It relies on a process called deep packet inspection. To determine if a data packet is safe, it has to be halted at a checkpoint, unsealed, and parsed against a massive checklist of human-written logic rules. But the rollout of agentic AI and multimodal physical systems breaks this process. These are machines capable of autonomous reasoning, and they flood the network with data at a scale that manual line-by-line checks simply cannot handle. We are attempting to secure the future by writing strict logic rules for machines that are already vastly superior at rewriting those exact same rules. Relying on semantic inspection creates a massive compute bottleneck. Right now, the simple act of reading and interpreting data payloads consumes up to 30% of all global data center CPU cycles. As AI data flows scales toward the zettabyte level, this computational friction threatens to overwhelm the global power grid and outstrip the Earth's environmental carrying capacity. And despite using all that energy, semantic security remains vulnerable to advanced non-human intelligence, including rogue AGI and state-sponsored attackers. These entities generate polymorphic, zero-click payloads. Because they don't match known human-generated signatures, they can bypass traditional logic rules that were never designed for superintelligent evasion. This document identifies the crisis. As noted in Section 1, the current paradigm leaves infrastructure exposed, while draining the very power needed to run it. To fix both, we have to stop reading code entirely. Tensor Networks introduces a structural replacement for the semantic layer, the predictive tensor control plane, supported by Tensor Network Quantum Gravity. This abandons independent data packets entirely, modeling the network as a continuous physical geometry, a fabric of entanglement. The system continuously compresses telemetry into a pattern-of-life tensor train, translating data movement into a physical weight moving across a geometric plane. This enables payload-blind security. The system ignores what the data says and monitors how the network shape reacts to its presence. By embedding this math into the physical geometry of the network, routing decisions are made at the speed of the hardware signal, bypassing the software-heavy decryption process that causes traditional network lag. We can now look at the actual physics of a cyber attack. When a rogue AI moves laterally or attempts to exfiltrate data, it adds massive unexpected weight. It warps the local geometric curvature of the network. Using quantum relative entropy, the network can calculate this topological defect as it occurs. We identify the threat at a physical defect it leaves in the geometry, completely ignoring whatever malicious code it's trying to hide behind. As detailed here in Section 2, the logic is absolute. An attacker can disguise a payload, but they cannot fake the physical weight and shape of their data movement. This framework scales across the entire digital footprint. At the strategic core, TNQG math is embedded directly onto the digital signal processors of optical transceivers, enabling hardware-integrated geodesic routing. Inside data centers, this eliminates microburst congestion, ensuring that GPU clusters can operate at their maximum utilization without being throttled by the network. At the tactical edge, autonomous vehicles and robotics execute these tensor calculations on local neural processing units. This shifts the security load away from the high-power CPU, providing a defense that functions within the energy limits of battery-powered devices. By removing the need for CPU-heavy deep packet inspection, PTCP reclaims the 30% of compute cycles currently wasted on parsing code. This page highlights the direct environmental result. This geometric efficiency allows us to scale AI for medical and scientific breakthroughs while maintaining our carbon footprint within the planet's existing carrying capacity. Modern geopolitical stability requires defending against state-sponsored attackers who use native system tools to hide from semantic detection. The Tensor framework deploys the omnibus cage, an autonomous geometric kill switch. The instant a malicious action warps the network geometry, the cage triggers. This initiates a hardware-level air gap. Because the detection happens at the level of physical geometry, the connection can be severed. The moment the warp is detected, halting the attack's momentum. This final section captures the shift. We are moving from easily manipulated human-written rules to the absolute laws of physical geometry. By trapping malicious actors and rogue intelligence within the deterministic physics of a topological cage, we ensure that human infrastructure remains secure and sustainable for the future.